continue to look at clay bricks, right, and we are looking at the properties I think related to burning condition. So, if you increase the temperature, compressive strength tend to increase. Normally, if you see Indian bricks, most of them will be somewhere there. It also depends upon the clay constituent, but for when the fire bricks which actually form the vitrification occurs at higher temperature, and you go to higher temperature. So, you go to 1200 degree centigrade, you might go to 25 or so, 25 MPa, right, which normally that kind of bricks you do not get much in India, but then higher the temperature. So, this is an observation. Second thing is, so increasing firing time of course does not have much of an effect. Including firing times does not have much of an effect, but at least 2 hours, minimum 2 hours or more, that is what is the burning time, keeping at the maximum temperature. Properties, other properties is the water absorption. This is the most important, and as we can understand, as the strength and this water absorption, which actually relates to porosity, right, total porosity. So, as strength burning temperature increases, water absorption reduces, and you can see the order of this is about 10 to 19%. So, porosity is corresponding to this would be even much higher, which will be around 30% or so. So, much higher porosity for these ones. Now, where do we produce them? We produce in Indian scenario, fixed chimney Bull's trench kiln. Kiln is a most one of them where we use, this is one type of kiln. Here product is stationary, the fire moves. So, the bricks are arranged in layer, we will see some photographs, arranged in layers, and the fire moves, burns and moves from place to place, and then of course, they are taken out. So, we have seen before that actually it is made into plastic state, then molded and dried, and then of course, this will happen. Then there is something called zigzag kiln, which is a variation of this one only, but now the fire will move in a zigzag fashion rather not in a straightforward fashion. Then of course, vertical shaft brick kiln, down draught kiln, and tunnel kiln. In tunnel kiln of course, product moves, fire is stationary. So, Hoffman's kiln, product stationary, fire move. This is actually after on Mr. Bull's name, who actually introduced this in Indian scenario. So, Hoffman's kiln is a product stationary, fire move. So, these are the types of kiln you have. So, we can look into each one of them one by one. So, fixed chimney Bull's trench kiln. This is introduced by one W. Bull in 1876. These are built above the ground by constructing permanent side walls and has a fixed chimney at the center of the kiln, right. Green bricks to be fired are placed in the annular space and covered with layer of partially fired green bricks as insulation, forming a temporary roof. So, temporary roofs are also partially fired green bricks, and layer of ash and brick dust is spread over the top to seal the kiln and to provide thermal insulation. So, essentially thermal insulation is provided by the roof, and this is how it looks like. So, the bricks are arranged in this manner. Air will enter from this side, the fire will move, direction of the fire travel. So, you actually will have the fuel together here. Fuel is also in the same arrangement, because you have got brick layers of bricks here, and the fuel is also there. So, the fire will move and the smoke will move out through the chimney finally. So, fire moves basically, and as it is fired, the bricks as it is fired, basically once the firing is over and cooled, bricks can be taken away. So, this is how the diagram, it is something like this, as you can see. So, these are the fired bricks, right. This is the firing zone. So, these are fired bricks, this is the firing zone, smoking zone where the firing is still going on, and this is actually at a higher temperature, and this is preheating zone, right. So, first preheating, then after this is, these are the green bricks, right, and there are entry point for the chimney. So, smoke can, for example, when it was burning here, the smoke would enter like this and reach there. Similarly, when it is burning here, the smoke will enter like this. So, loading and unloading area is this. So, here this will be actually, this is green bricks loaded in this manner, and fire bricks are taken out from this manner. Fire bricks are taken out, fired bricks are taken out from this manner, right. So, this you have preheating zone, firing zone, smoking zone, and there is a cooling zone here. So, once cooled, this can be taken out, and loading and firing area. There are some open gates through which you can go. So, they are arranged, and the fuel is also there together. So, as you burn, they heat up, and that is how it goes, right. So, this is that fixed chimney Bull's trench kiln that was introduced in 1876, and possibly many places still it is used. An improvement over this is fire flows in a zigzag path instead of the straight path that is followed here. So, if you see in this one, this was fire was moving in a straight path. In this kiln, the zigzag kiln is considered an improvement over this FCBTK, and higher heat transfer rates between the air and the bricks due to higher velocities and turbulence caused by zigzag path, frequent change in direction. So, since if you change in direction, obviously the turbulence will be created, and the basically local velocities could be higher, and that's what efficient burning. So, this gives us improved combustion due to better mixing of the air and fuel in the combustion zone, and longer time available for volatile in the combustion zone, right. Shorter length of the kiln and hence smaller footprint, because the length now it is zigzag. So, you have you can same length you can cover in a lesser area. So, that's the idea. So, it is an improvement over the previous one, it is an improvement over the previous one. The Bohrer zigzag kiln was similar to Hoffman's kiln in construction. Draught can be created by fan or natural draught using chimney. So, basically chimney also creates natural draught. Hot gases will tend to go, cool gases will come in. In this one, this is how the fire would move, right. So, the path would be something like this. So, bricks would be laid in this manner. So, that the space here it will move in this manner. So, this is how the travel to the kilns, I mean the hot air or the fire moves along in this manner, right. So, this is an improvement over the previous one. Then there is something called vertical shaft kiln. It has got a vertical shaft of rectangular or square cross section. The shaft is located inside a rectangular brick structure, right. So, the brick structure itself and the shaft is there. The gap between the shaft and the wall and the outer kiln wall is fired with insulating material, is filled with insulating material, clay, fly ash or rice husk ash or similar sort of thing. So, in the previous one you will have actually in both these cases you will have this roof covered with partially burned green bricks, and then some ashes or something at the top to make a kind of insulation on top of it. So, both this one here the same thing you can see, this is now vertical shaft that we are talking about is a vertical shaft kiln. So, heat exchange takes place between the air moving up continuous flow and the bricks moving downward intermittent. So, you actually feed the brick, they go downward, hot air goes upward, and this is not continuous. Obviously, airflow is continuous, but the brick movement is not continuous. So, let us see some diagram. Green bricks are loaded from top in batches. So, bricks move down the shaft through brick preheating, firing and cooling zones and are unloaded at the bottom. Now, the combustion powered by coal put along the bricks at the top, right. So, as the hot gases go up, they will actually ignite the coal themselves, and simultaneously firing will occur as the your loading, intermittent load is going downwards. So, it takes place in the middle of the shaft. Air for combustion enters the shaft at the bottom and gets preheated by hot fired bricks in the lower portion of the shaft before reaching the combustion zone. So, this is how it looks like. Green bricks are loaded from here, in some sort of supporting system tray or something of that kind, and this itself is a firing zone. Together with this, I load also the fuel. So, fuel is also loaded, and the burning is continuing. As the burning is continuing, hot gases, hot air would move through this, hot air would move through this. This air will ignite this fuel and burning will take place here. So, once this is intermittent. So, you hold it for certain period of time during the burning time, and then this whole thing comes out. So, flue gases will go out from the side and then it is unloaded from the bottom. So, hot flue gases preheat the green bricks. So, naturally if it is this is going through this. So, this can also preheat the green bricks in the upper portion of the shaft before exiting from the exiting from the kiln through the shaft of the chimney. So, this is the shaft of the chimney, through that this will go out. So, this was vertical shaft kiln. Then you have down draught kiln is an intermittent kiln. One batch of bricks is fired at any given point of time. So, this every the kiln is first filled with green bricks. It is then fired, and this is then fired, and batch is heated up to the maximum temperature and left to cool. So, in the process of heating, the kiln structure also gets heated up, and while cooling, the stored heat in the structure is lost due to atmosphere. So, this, as we shall see, the energy part of it. So, these are the processes, but then we will look into the energy part of it. We will see that actually the efficiency of this system, because a lot of heat is lost. You first burn them, and then you got to cool it before you load it. So, cooling means the heat whatever was there is actually wasted downwards. So, intermittent kilns, this one down draught kiln, which is intermittent, though being suitable for small scale production, is not fuel efficient. In down draught kiln, fuel is burnt in external fuel boxes provided in the outer periphery of the kiln. The hot gases from the burning fuel rises to the roof of the kiln. Gases, after being deflected from the roof, flow down through the brick setting in the process, warm and fire the bricks. So, the bricks rest either upon open work support or previously fired bricks. That means, you might have a kind of some sort of a support system built in there, which will remain there and support the bricks on top of it, or upon some perforated floor. So, that hot gases can go, hot gases can move upward, and flue gases through perforated floor, through which the flue gases flow down into the underground channel, which is connected to a chimney, and are exhausted through the kiln itself. So, the warm gases rising through the height of the chimney provide sufficient draught to pull the hot gases down continuously through stack of the green bricks. So, this is how it looks like. This is the chimney somewhere outside. You have the bricks, right? This is the chimney. So, every there is a kind of a perforated floor. So, basically as we have seen earlier, the total cycle required for, this is separate. This is what we have said is the bricks, they rest of course in some sort of perforated floor, and the hot gases flow down into an underground channel. So, what you are doing is you have basically fuel is burnt in the external fuel boxes provided on the outer periphery of the kiln. That means, it will have something here, some places here the boxes where it will burn, the heat will be supplied through this, they will burn and the flue gases will go out like this. So, cycle time, there is a cycle time because it is intermittent, not continuous. So, it is around 7 to fired bricks as 7 to 7 cooling, loading to green, from loading green bricks to cooling, it takes about 7 days or so. This is most common, you find them very commonly in many places, because small kilns are of this kind, but not so efficient. In tunnel kiln, which is horizontal moving wire kiln, bricks to be fired are passed on cars through a long horizontal tunnel. So, the firing zone remains stationary. So, these cards will move, hold into the firing zone, held into the firing zone. Once the firing is over, it is taken away and then the next lot will come in, where the bricks and air move in counter directions, because cool air will move in one direction, hot air will move in the other direction. So, the green bricks get a little bit of preheated. So, cold air is drawn from the exit of the cart and cooling, they will cool the fired bricks and preheat the previous bricks. Combustion gas is travel towards the car entrance, transferring part of the heat to the incoming green bricks. So, the cars can be pushed either continuously or intermittently at fixed time of intervals, that is what is done. And the tunnel kilns have provisions for air extraction and supply at several points along the length of the kiln. So, this is how they look like. There is a cart, right, this is green bricks. So, this is loaded here, this is its position, okay. This is the position. So, flue gases comes from, the firing is occurring here and the air comes from this side, right. So, this air, the air gets, this gets, air, this is the trolley car, the air, hot air, cool air comes from this side, some of the hot air go to dry air and then this follows, and flue gases will actually preheat the green bricks. So, this will movable basically. So, that is the types of bricks. So, this is what it could look like. You can have a chimney here, the scrubber, green bricks comes like this, the hot air flow, right, and this is a kiln. So, just basically the hot flue gases and all that. There is a fan here, there is a fan here which can drive it out and air flow through this, right. So, the firing occurs in the talent kiln here and the fired bricks comes out like this. So, this is the kind of bricks you have, processes. And first of all, the clay bricks, we use a lot of alluvial soil, clay you have to take from. So, therefore, land is also, you are occupying certain amount of land. Otherwise, if it is, let us say, blocks of some form, if it is from waste material like fly ash, then of course, this is most advantageous. But however, this is still there, very much there in practice in some parts, definitely in India, there is definitely is there. So, we talk in terms of what is called specific energy consumption. It is the thermal energy required to fire 1 kg of brick per kg per unit. So, specific energy consumption we are talking of. Then we talk of environmental performance. So, this is one issue is this, the energy consumption issue. Other issue is environmental performance. So, emission measurement for particulate matter, black carbon and selected gaseous pollutants. Then obviously, the financial performance in terms of capital investment, cost of production and how we get the return. So, these are 3 performances one looks at. So, if one looks at the average specific energy consumption in megajoules per kg of fire bricks for various kilns, the fixed chimney Boole's trench kiln, it is of the order of around 1.2 megajoules per kg, whereas zigzag will have slightly less because you have an efficient system relatively, and then vertical shaft kiln is somewhere there, and this is the downward dot kiln and this is the tunnel kiln, and this is the most efficient. You can see vertical shaft kiln, which one we discussed earlier, if you remember, vertical shaft kiln, not this, down dot kiln is one of those worst type, vertical shaft kiln, not this, down dot, not this, vertical shaft kiln, this is what we talked about, and this is the most efficient sort of from energy point of view, energy performance point of view. So, vertical shaft kiln, they are the one most efficient, they are the most efficient. So, vertical shaft kiln, this is in Vietnam, this is in India. this is in Vietnam. So, that some people collected the data on those kind. So, in Indian scenario, Vietnam also is quite popular, and apparently they have some sort of relatively more efficient system, but however, amongst all this, vertical shaft kiln is the better one, or it uses least energy. So, of the order of around less than 1 megajoules per. Main source of energy input is the firing coal. Earlier people were using timber also. Potential heat of combustion, combustible matter in green goods, obviously that would be there. Heat stored in the kiln at start, and main source of energy output is a sensible heat at maximum temperature, right. So, heat used in the endothermic reaction that occurs, the vitrification where it forms solid solutions, there the chemical reaction I told you about earlier in the last class, that is essentially the silica, first one, obviously the water smoking would occur, free water will go away, then in the water bound in the silicate and aluminate system, that goes away, forming the new product. If you remember, we talked about the chemical decomposition of the clay product, forming into a new fused solid solution, right, a new kind of compounds, and that in the process actually initial process was endothermic, it will take a lot of heat. There is an exothermic component also, but main is the heat is used in endothermic part of the reaction, like breaking the decomposition of the clay themselves, So, main losses are stored heat in fired bricks itself, right, after the process, and also flue gases goes at higher temperature. So, there are some losses from there also. Environmental performances are measured in terms of suspended particulate matters, right, suspended particulate matters, that is particle with diameter less than 100 micron, and that tend to be airborne. So, particulate matter 2.5 is basically the fine particulate matter, diameter less than 2.5 micrometers, can penetrate deeply into lungs, and it also has a longer atmospheric lifetime and disproportionately greater effect on visibility and climate. That is what they say, that because these particulate matters, they come from burning, right, burning of the fuel that you use in kilns, and since their particle size is very small, they remain suspended for a much longer period of time, and they can they can actually they can penetrate through your respiration process into the lungs, and they are dangerous. So, PM2 from coal combustion contains some mineral, but also large quantities of carbonaceous aerosol, right. So, aerosol are the fine particles that can remain suspended in the air. So, that is what it is. So, also like black and organic carbon, which you can measure through optical measurements. Black carbon is a combustion product predominantly composed of strongly bonded graphite like carbon rings. They are very fine material, aerosol form, and this composition causes black carbon to be thermally stable at high temperature and strongly absorb, they can strongly absorb visible light. So, when you are heating black carbon, it can absorb light and it is stable at higher temperature. So, that remains while your vitrification occurs. Organic carbon of course comprises of all carbon species that are neither black nor carbonate carbon. So, they are all carbons, that is what you call it, organic carbon. So, they are not necessarily all will be suspended in air, but black carbon are the ones which can be. For comparison, grams pollutant per megajoules of fuel rather than per kg of fired brick is used. So, we have used specific energy in terms of per kg of brick, but when it comes to pollution, right, we look into per megajoules of fuel, because it comes from the pollutant comes from the fuel, not from the coal. So, if you are using more fuel, more specific energy consumption is more, so obviously the pollution also would be more. Then there is something called emission factor. Emission rate is expressed in kg per hour. Emission rate is expressed in kg per hour. So, kg per hour, which is S is the pollutant concentration, right. So, emission rate you talk in terms of pollutant emission actually in milligrams per cubic meter, and Qs is the flow rate. So, if Qs is the flow rate from the chimney and S is the pollutant concentration, then this would be S into Qs 10 to the power minus 4, because this is in kg per hour and this is in milligram per cubic meter, and this cubic meter per hour. So, milligram you got to convert into kg, milligram you want to convert into kg, right. So, cubic meter hour, this is in cubic meter hour straight away. So, milligram would mean how much? 10 to the power minus, yeah, but minus, this cubic meters will cancel out, milligram per milligram since 10 to the power minus 3 and then 10 to the power minus 6 kg. This is why this is 10 to the power minus 4, it is not definitely not per meter square. So, this is kg per hour, S is pollutant concentration in milligram per cubic. So, if I simply multiply S by Qs, I will get milligram per hour, which is converted to minus 6 actually. So, anyway, we will come across this again. Emission factor in grams per kg is given as with F as the burning rate in kg per hour. So, if my burning rate is F kg per hour, emission factor is emission rate divided by F into 10 to the power 3. Emission rate divided by F into 10 to the power 3, right. So, emission rate is in kg per hour, emission rate is in kg per hour and this is in kg per hour. So, this is simply a dimensionless quantity, right, it is dimensional, but it is given in terms of multiplied by 10 to the power 3, because this term would be relatively small. So, this is grams per kg, one of them is in grams per kg. So, 10 to the power 3. So, emission this in grams per kg. So, this would have been kg per kg multiplied by 10 to the power 3. So, this this emission rate is in kg per hour, this is also in kg per hour, but this is multiplied by 10 to the power 3, because this is expressed in grams per kg, this is expressed in grams per kg. So, this should have been what? This should have been kg per hour divided by the burning rate kg per hour, again kg per hour. So, this is expressed in grams per kg, this is emission performance is expressed in is grams per kg, burning rate of fuel, and this was pollutant concentration kg per of the flue gases. So, this is the multiplying factor of 10 to the power minus 3 coming here, because I think it is converting into kg to gram somewhere. We will see that, actually, it will come out through. So, emission factor on the basis of energy is grams per megajoules. So, EC is the energy input megajoules per hour, which is given like this, EFM ER over EC into 10 to the power 3. So, you can talk in terms of grams per megajoule rather than grams per kg, but in that case this will be EC is the energy input megajoules per hour. So, product of EFM and SE gives performance, emission factor performance, product of this ER by EC, SEC per kg of brick, because this is expressed in terms of megajoules per kg. So, and this is in terms of megajoules per kg now, and therefore, you can express in this manner. Then the other issue is carbon balance. F of course, is from the fuel, because burning of fuel will produce carbon dioxide, it will also produce carbon monoxide, some hydrocarbons might be left and some carbon in some particulate form like carbon black, etc., etc. So, if you know the carbon in carbon dioxide, that is known, carbon in carbon monoxide is known, and carbon in type of hydrocarbon it will be known, and in particulate matter concentration of carbon if it is known, then we can find out how much is the carbon in unit fuel, unit, we are talking in terms of cubic meter per hour. So, that is what we can find out. So, Fc is the fraction of carbon in the quantity of fuel consumed and is the sum of fraction of carbon in components, right. So, carbon dioxide is totally, if I am looking at carbon dioxide alone, then Fc is the fraction of carbon in the quantity of fuel consumed and is the sum of fractions of carbon in all the components which have carbon. So, there are 4 components, that is carbon dioxide, carbon monoxide and hydrocarbons and particulate matter which can have carbon. So, Fc is the fraction of carbon in the quantity of fuel consumed, right, and only in these 4 components I have got carbon. So, this is the fraction of carbon as far as carbon dioxide is concerned, this is in carbon monoxide, this is in hydrocarbon. So, carbon dioxide therefore would be Fc minus all this, because we are interested in the carbon dioxide. So, Fc divided by quantity of carbon dioxide is written something like this, Fc, this is written is in terms of a term K. So, one can find out the carbon dioxide Fc plus 1 by K, where K stands for proportion of carbon monoxide to carbon dioxide, proportion of hydrocarbon to carbon dioxide and proportion of carbon in the particulate matter with respect to carbon dioxide. So, this gives us F. So, if you know this Fc, one can obtain how much carbon dioxide is produced. Okay.